Alright guys, so if I remember correctly, I think we only got one formula kind of set, even though we did a lot. We haven't gone back to formalize what we did yet. And the funny thing is, you're just going to agree with me all day? Yeah? Okay. We did a lot of probability problems without any formulas because when I give you the whole situation to count, you don't need formulas. So very often the formula gets in your way. So I'm going to try to make it really clear when you don't need a formula and when you desperately need a formula. Because very often people try to force the formula and it just isn't going to work. You're not going to use it correctly. So if you can just count stuff, dear God, do it that way. This probability is pretty simple. Very simple idea. So what we've done so far is really all we really did as a formula was this formula here. A given B. So this is A given B. So which one do you know happened? Do you know that A happened or do you know that B happened? B happened. What's the probability of A? What's the probability it's a man given that they came off of a Harley Davidson motorcycle? Right? That was the situation we talked about last time. So this part is what I know happened. So I can throw out everything else. So on the bottom, it's not going to be everything. It's just going to be those things related to B. That's how you know it goes on the bottom. The given thing is on the bottom. Let me stop there for a second. This is what we did last time when we had the table. We threw everybody else out, and on the bottom only went the total of how many what was I was given. That was a sentence. So last time we did something where we had this little table. Let me make a little quick one. A little tiny one. No maybes. We said you can't say maybe. 3, 5, 11, 2. Very quickly here. So if I add these up, get the totals. If I said what's probably I pick a woman out of this group. 13 out of 20. So if I don't know anything about the person or the thing that I'm picking or anything about the situation, the bottom's going to be everything that could have happened. If it's a deck of cards with no jokers in it, it's going to be out of 52. Because it could be any of those cards. This could be any of these people. 13 match what I'm looking for divided by 21 people. But if I say what's probably it's a woman given that they said no, what's going to go on the bottom now? 7. I almost gave it away. It's going to go on the 7 now. That's good, Jeff. On the bottom is 7. Why? Because how many people said no? Because I'm given that they said no. So who could it be? Only any of these 7 people. That's who it could be. It can't be any of these 21 people because those people said freaking yes. We're throwing them out. You said yes, get out of here. So out of those 7 people, how many are women? 2. So you can see how the probability might change if I'm given some information. Given that you're under 21. What's the probability you're in a car accident? Higher. That's why insurance is so high for people under 21. Oh, drive better. All right. Improve the statistics. Yes?
So there was a question in the 3.1 homework, like the first chunk, and it was like without the equation, just like P is the P of A given B. But it didn't, the way it worded didn't make any sense.
Do you remember what number it was?
Like, one of the first ones with the men with short hair, women with long hair, or whatever.
Oh, okay. They just wanted you to write what it would look like.
Yeah, but there was, I don't remember which one it was exactly, but the format was the given one.
Okay.
But it was worded where the word given wasn't used at all.
Oh, okay. If I said of all the people who said no, what's the probability it's a woman? Of all the people who said no, what's the probability it's a woman? Isn't that this? Out of all the people who said no. So it doesn't have to expressly use the word given. If I said, okay, out of all the women, okay, given that it's a woman, you see I can reword it to use the word given. So given, normally we use that word, but sometimes we don't have to. We can say out of all the people that like cheese. So everybody who doesn't like cheese, I'm going to throw you out. We're only going to look at the cheese lovers and say, what percentage of them eat at Taco Bell? Whatever. Right? And how do they feel a couple hours later? All right. What should go on the top of this? Why was this only 2? There's 13 women. Why is this only 2?
That's the women and the men.
Yeah, there's only 2 women who said no. The only way that they could be a part of this is that if they said no, because the only way you can be a part of this period is if you said no. Because I'm given that they said no. Yes, ma'am?
What about when it has an or?
We're getting there. So, this is the only formula we've come up with yet. We've done more than this, we just haven't written the formula down. Because again, you can do a lot of probabilities without any formulas. In fact, we just did that one. We really didn't use the formula, did we? No, we didn't. We don't have to, because I can count. I only use the formula when I'm only given the probability of A given B is 0.7. The probability of A and B is 0.3. What's the probability? Oh shit, now I got to use a formula and plug stuff in like in algebra. Just plug values in and solve. So we'll see a problem like that here in a little bit. Actually, let's see a problem like that right now. Why not? I don't know, Jeff, why not? Oh, high-tech eraser. So what if I said the probability of A and B is 0.2. The probability of, let's see if you guys can handle this. Oh shit. The probability of B given A is I gotta make this actually make sense. Sure, Jeff. Don't worry. 0.6. What's the probability of A? Oh, I like it. Okay, now. Well, I like the looks I'm getting. First time we're doing a problem like this, right? So don't look concerned yet. Look concerned if we do a few of these and you still don't get it. That's when you look concerned. What is this a formula for? A given B. What am I given? What information am I given? I can't say any other words. B given A or shit. So what's the formula look like for that? Probably B given A equals what goes on the bottom? B of A. Yeah, which is the same as A and B, so it doesn't matter really. All right. That's the first thing to realize is just because I put an A there and a B there, it could be a D and a C. And then wherever you see an A, you put a D and C and whatever. It doesn't matter what the letters are. Just like in algebra, it doesn't matter really if you use X or Y or A or M. No. They're just dummy variables. Now you just plug in what you know. What do you know? Probably B given A is 0.6. What do you know over here?
B and A is.
Yeah, A and B is 0.2. And I'm looking for probability of A. This is the most algebra you would see in this class. There will be a few other times where you like move some letters around. Ooh. If you can't handle this, this is bad. This is bad news. For me and how do you solve for P of A?
33%.
Yeah, how do you solve? What do you do?
Multiply P.
Multiply it up and divide that down. These really just switch places. Let me stop there. There are chairs in the front if you're having trouble. There's 1, 2 there. Okay. Is that cool? Did you guys see that? Yes, ma'am. So why is this PB? Because what's given? B. Why is this PA? Because what's given? A. I like it. And then you would get 33%, like 33.3, 1/3 there, right? All right, let me. So two things. How would I write? What would probability of D given M? What would that be? What's on the bottom? P of M. And what's on the top? D and M. All right, now do you see how it doesn't matter what letters I use? It doesn't. This is the idea of it. Whatever's here is on the bottom. Why? Because whatever's here is what I know happened. So it's got to be out of that. And what's the only way that it could be in B and A? Well, if it's in freaking B and A. So that's the top. Whatever the B and the A are. It doesn't have to be A and B. It could be D and M. It could be B and A. The other way around. Okay. Is everybody cool with what happened from here to here? All right, good. This is a good question. See, that's where you ask a question. So let me focus on that. What do you do anytime you have your variable on the bottom? Multiply by. So I have 0.6 times P of A equals 0.2. Is that cool? You know this from algebra. Anytime your variable's on the bottom, that sucks so desperately bad. So you multiply it and get the hell out of there. Because trying to solve for it. It can't be on the bottom. And now, what do you not want over here? 0.6. Now, what's really cool to learn from algebra is this little truth. If I have this equals that over that, I can just change these. And that feels like you're cheating. But tell me, what is 10 divided by 2? That's amazing. If I change these, is it still true? Of course it's freaking true, right? 10 divided by one part is the other part, so 10 divided by this part is the other part. So that divided by P of A is 0.6 would mean that divided by 0.6 must be P of A. Together they make it. I mean, so you can just change those. It's a beautiful, quick trick to learn from algebra. Or solve it like this. So then you do get P of A is 1/3. Or 0.33333. Okay, maybe. Because I can do and then I can reduce that. You can do whatever sound effects you like. You don't have to do Alright, maybe. I love how all of you guys went, algebra? I passed algebra. Yeah, well, you passed algebra, you should be able to freaking do it. Oh, shit. Alright. Let me think. So you're going to see some problems like this. There's going to be some problems like this on the worksheet today and the practice quiz and the actual quiz. Oh, snap. Yay, stuff. Okay. So we need to go back and get the other formulas that we're going to have to use. One formula was related to, do you remember when we did this? I said from a deck of cards, what's the probability that you get jack or a club? I said we did something like this. You get a jack or a club. Well, how many jacks were there? 4. How many clubs are there? 13. Rams. But what's wrong if I do this? Something's wrong with that. I double counted. Who did I double count? Jack of clubs. The jack that is also a club. The card that is jack and club. So I better do what? Yes, subtract everybody I double counted. And then you do that and you get this and you can do crap with it. But I want to look at this and get the formula, the general formula for this. So the probability of A or B. What was 4 over 52? What's that related to? That's the probability of what from this problem? Jack. So the probability A or B is equal to the probability of A plus the probability of B minus all those that are where? That are both. Minus the probability of A and B. So we developed that formula based on what we did with the numbers that we could count. So again, this is an example of we had a problem that we did before we even knew the formula. So if I give you a situation where you just count stuff, it's cards, or it's poker chips in a bag, or it's in a table like the one we did yesterday or earlier today, I would highly recommend you don't even use a formula. You just do it. The only time you really need a formula is when you have one like we had just a minute ago, the 0.6 and the 0.2.
That wouldn't be divided by a number.
No, P of A is 4 over 52.
Okay.
All right, the over 52 is built into each of these.
Okay.
Good, I like it. So OR basically means add. See how I got real slow in my talking there? Normally when I do that, it's a hint, it's a big note to take. Or basically means add. And I say basically because there's a little bit of an adjustment if they overlap. So what's the probability of, if I do a deck of cards again, what's the probability I get an 8 or a 9? How many 8s are there? 4 of them. How many 9s are there?
4.
So 4 and 4 is 8. Do I have to adjust it at all?
No.
Because there are no cards that are both. You know, or if there are in your deck, I'm not playing cards. Telling you, I got a full house now. Now screw you. 8 and 9, yeah. There's no cards that are both 8 and 9. Does that make sense? So in this case, what is the probability of 8 and 9? So that would mean a card that is 8 and 9. So what's the probability of that happening? 0. So that's why the formula is still true. I'm just subtracting 0. The probability you get a card that's both of these is 0. That's why there is no minus there. There's no adjustment to make. So that's what I mean here. It's basically add, but there's an adjustment if there's any that's both. Yes?
Would there be any that's like keys 8 or 9 or club?
Yeah, and then you just keep going. You could. Now that gets a little bit worse to handle, especially when there's multiple overlaps, right? So in the entire world, yes. In our class, no. Okay, I like it. Because when there's multiple overlaps between multiple, oh my God, you don't want to go there. And we won't go there. All right. Now, do you notice a trend here? So I got this formula, I've got this formula. There's at least one more formula I got to get, and both of these formulas depend on it. Both of these formulas depend on this thing. What is it that I don't have a formula for that they both actually depend on? Probability of what? That depends on the probability of A and B. That depends on the probability of A and B. Do I have a formula for the probability of A and B yet? Shit. That seems kind of crucial. Let me let that sink in a little bit. Okay, so here's my 2 attempts at explaining how AND works. Okay. The first attempt is a silly example, and we're just going to go with it, because that's what you do. You know, like we go with whatever the hell you do, Jeff, because we're captives. You can do whatever the hell you want. Okay. So let's say there's I want to join a fraternity, right? Thank God this is not true, but say I want to. And they have this hazing that's not anything crazy. What they do is I have to walk down this hallway, and every 5th step I take, somebody slaps, bam, right there. Right? And every 3rd step I take, bam. You with me? And I'm blind. I'm like, oh, shabam, oh, shabam. So how often? So what percentage of the time will somebody slap me on this cheek? Every 3 steps, right? So what percentage of the time? 1/3. I like it. So probability of left cheek is 1/3. What's probably a right cheek? 1/5. Now, what's the probability I get slapped on both cheeks at the same time? How often will that happen? Every how many steps will that happen? You can do this.
15.
15! You guys all see that? Oh, it's LCD. LCD. No? All right, let's step it. Let's step it. All right, 3 steps. All right, somebody help me out. 1, 2, slap. 4, 5, slap. 6, slap. Right, every three, it's a slap. Every 5, it's a slap. So where they meet is like LCD, isn't it? But what is it? How do I get 15? What do I do with these numbers? Multiply them. Now, this is not a perfect example. Don't read too much into that example. But it basically is the idea. If I want probably a left and right, I multiply. All right, we're going to see in a minute that there's more to this story. Somebody slapping me on this cheek, does that change the probability somebody slaps me on that cheek? No. They just have their job. They're like counting my steps and they come, smack! I'm like, man, jeez, all right, do I want to be a part of this? All right, so here's another example. when I was a little kid, I lived in Florida, and we would go out and watch the space shuttle take off. Right? It was awesome. We would go out, we could see it take off. The one time we didn't go out is when it blew up the first time. I hate that I have to say the first time. Back in '86. I was a little geek, and we were sitting in class, and we heard about it, and I just started crying. Oh, I just started crying. It was huge to me. But I don't know if you know why the Challenger blew up. Why it blew up back in '86. There were these things called O-rings. We're not going to get into the physics, but there's these things called O-rings that are basically like valves, making sure the gas goes in the right direction instead of in the wrong. And they had frozen up and so forth, and so they didn't operate correctly. But you have several of them in a row, just like you might have several locks on your door. If you live in a worse neighborhood, why would you do that? Because you want to decrease the probability somebody cracks all of them. Right? You can get this kind, but can you get this kind? Yes. Oh shit, can you get this kind? Yes. Oh shit. So that's why you have multiple locks, right? Does that make sense? Contingency plans, right? So let's say there was now this is not true, thankfully, but just to make the numbers a little bit easier, let's say there's a 1% chance that any individual O-ring will fail. Now hopefully, if I put them both in the same pipe, I don't add them, because then that doubles the chances they fail. That doesn't make any damn sense. If the number of locks I put in there increased the probability somebody got in, I'm not going to put a lock in there at all. Does that make sense? So somehow they should decrease. So if I were to fly the shuttle 100 times, how many times would I expect this one to fail? 1 out of every 100. Now, out of those times, how often will this one also fail? 1 out of 100. Now, 1 out of 100 of 1 out of 100 times they will both fail. What does of mean with multiplication? With fractions, it means multiplication, right? Yeah. So I multiply. Does that start to make sense? If half the time I did something and 1/3 of the time somebody else did something, how often do we do it together? 1/6 of the time. 1/2 of 1/3 of the total time we would do it together. So 1/6 of the time. So and basically means multiply. All right, so let's do a concrete example, and then we'll actually get a different formula. So going back to cards. What if I pick 2 cards? How's this guy doing? He's got very little battery.
Has a little silver thing.
He's good. All right. Pick 2 cards. Let me see if you guys understand. If I pick 2 cards, I could throw that one away, or I could put it back in. Now listen. How many cards are there when I start? 52. If I threw it away, how many cards are there now? And all the probabilities are going to change, because now there's only out of 51. Oh shit, so let's start with replacement. That way everything's out of 52. Is that cool? You know, like, I don't know, man, just do it. Does that make sense? If I do it without replacement, if I feed it to my little brother, then I've got less cards, all the probabilities change, because now they're all out of 51. Oh shit, we don't want to go there yet. So let's say I pick 2 cards with replacement. What's the probability I get 2 kings? Well, what's probably that the first one is a king? 4 to 52. And times, so I take that one, it's a king, that happens 4 to 52 of the times, right? I put that back in. And now I want the second one to also be a king. What was the probability the second one is a king? Still 4 to 52. So this is how you use this idea in practice. If I'm going to do multiple things, I can multiply each of the probabilities together as long as they don't affect each other. So we need to talk about that a little bit more. And if you do this, you get 1 out of 169, which is whatever the hell it is. Nobody's going to help me? Okay. We'll just live with that. And which is whatever it is, as a percentage. 0.5% almost?
It's like
0.6. So 0.6%? No, yeah. So it's 0.06? 0.06? Okay. Yeah. Alright. Now, how would this change if I said without replacement? Let me put this up here. So I want to do that same thing, 2 kings, but I want to do it without replacement. I pick the first one, and I throw it away. And hit somebody in the head. Or I'm gambling. Alright. Or not. Alright. This is a little too geeky for the scratch. Alright. Good. So if I do this without replacement, I really want this to make sense. The probability I get a king, let me make it a king, and then another king. Because the word "and" sometimes gets hidden. If I say the probability of 3 boys, that's a boy, and then a boy, and then a boy. We wouldn't say that in English, so the "and" gets hidden. Okay, maybe. So what's probably the first one's a king? Well, still, 4 out of 52. And I throw that one away. What's probably the next one's a king?
351.
3 out of 51. Why did the next one change?
Because you threw out the 1 point.
So this, I really want this to make sense. That number is not, this is definitely P of king, right? That's definitely the probability of a king, right? Is that also the probability of a king? No. That's the probability of a king given, I picked a king already. Alright. It lets you write what you want from that. Stay with me. Does that make sense? How do probabilities change if I'm given more information? Yeah. Because what did I pick first? A king. And I threw it away. So what did I lose? I lost a king and I lost a card. So that's why that became 3 over 51. I like it. I like it. Do you like it, Jeff? Yes. It is light. Okay? And then you get whatever the hell you get. I don't know. Somebody wants to do that?
0.004.
3 over something, and which is point.
0045.
All right, I like it. So the probability went down. Why does it make sense the probability went down?
But there's less.
It's not adding really. If I want 2 kings, and I pick a king and throw it away, the probability to get another king just went down. So 3 out of 51 is smaller than 4 out of 52. If you try it, if you do it. So it makes sense that the whole probability went down a bit. Because I lost the king on the second when I'm about to take the second card. Alright, I like it. Alright, let's do this. I want to show you this. So here, why did I not have to change the second one?
Because it wasn't without replacement.
Because the first one being a king, did it affect the second one at all? No. We would say those are independent events. One happening didn't change the other one. Here, that definitely changed because I lost a card and I lost a king. So this is what I would call this dependent events. Because if one happens, the other one changes. Does that make sense? Independent events means if one thing happens, the probability the other one doesn't change. You're like, I don't care. You do what you want. I'm independent. Dependent means if one thing happens, the other one does change. You're like, oh shit, you changed? Oh shit. Oh God. Just like I said, if I saw somebody get off of a Harley Davidson motorcycle, the probability of their man just went up. It went from 50% to who knows. So they were dependent events. Okay. Maybe. So what I want to do is, I want to write the general formula for an AND from what we just did here. Probability A and B. So probability of a king and then another king was the probability of a king, probability of the first dude, times the probability of this guy given that the first guy happened. Because what happened? What's the first thing that happened? A. So what's the only way B can happen if A happened already? So probability of A times the probability of B given that A happened already. Alright, so let's do another problem with the cards. What's the probability that I get an 8 and then an ace? without replacement. So what's the probability of an 8? 452. Any card is 452. Now what's probably, I take that and I throw it away. Yeah, what's probably getting an ace? 4 aces still out of 51 cards. I like it. So that is the probability of 8. That is the probability of 8. This is the probability of ace given that I got an 8. That's why the number changed. I got an 8 and threw it away. So now we have basically our complete set of formulas. There's really just 2 more ideas I want to talk about, and then I'm going to unleash you on this worksheet, see what the hell happens. Everybody's writing something, or they're drawing something. I don't know. Okay. I think this book calls it. Please, book. Yes. Okay. Good. Screw that other word. My old book called it disjoint. It's crap. If 2 things are mutually exclusive. So what does exclusive mean? What comes to mind when I say exclusive? Oh, I see. Like, well, you're thinking about